Next is Andrey Gurevich, talking about less is more. Andrey, I'm welcoming you to join us. Andrey is an algorithmic team lead at Mobileye AI engineering group. He did his MSc in electrical and computer engineering from Ben Gurion University, and it's a pleasure to have you here with us today.
Hi, thank you. So I'll present our work, Less is More, Selective Layer Fine-Tuning with Subtuning. This work was done as part of our research in Mobileye with those following people. So what we'll talk today? First, I'll present some motivation about the research. Then I'll talk about fine-tuning profile and the algorithm itself, subtuning, the algorithm, its work, and multitask learning. So let's start with motivation. How are we training deep neural networks? So we have a few ways to do this. Let's start with the basic methods. So the first thing that we can do is train from scratch. This requires a lot of data and also has low performance. We also can use a pre-trained model which will allow us to get more rapid convergence and better performance. And we can do this in few ways. So we can use this in train a new head on this model. This is very fast and but has low capacity. We can also do a fine-tuning, which will have better performance, but it's very costly on data and compute. So in first case, we'll train just a new head, but in a second case, we'll train everything together. We also have other methods, which is head-to-toe and LoRa, which I will not talk about today, but we compare to them in the paper. Great, so let's talk about the fine-tuning profile. So we ask ourselves, what if we fine-tune only a subset of layers and not all the layers? Maybe this way we can achieve the benefits of all worlds for a network. So what we're doing here, we're just taking the network and we're training only one layer at a time. And we're also training the head, obviously. So how will it look? So if we're talking about ResNet 15, it has 16 blocks. 16 res blocks on 4 different resolutions. So the fine-tuning profile will look something like this. On the x-axis, we have the number of blocks that we're fine-tuning, and on the y-axis, we have the performance of this block. Okay, so what we can see is that not all layers are created equal. This means that if we subtune a different layer, we get different performance. In this case, training the 14th layer gives the best results. Okay, so in order to get optimal performance, we need to perform this fine-tuning profile on many datasets. But we noticed that changing the target dataset, the target task, or the architecture or the pre-training affects the performance. And we can see this in the following graphs. So we did it on both ConvNets and transformers, and we did it on many different datasets and many different pre-trainings. And we can see that the profiles are different for every case. Okay, so let's talk about the algorithm. So subtuning. We want to fine-tune only a subset of layers and not the whole network. This is where the name comes from, subset tuning, subtuning. What we're doing, we're just selecting the best layers to fine-tune. This is done via the fine-tuning profile I talked earlier, but this can be very costly. So I'm showing here a plot which does it for 2 blocks. This can be very costly, so what we're doing, we're using a greedy algorithm to reduce cost. Basically, it's very simple. We're doing this iteratively, picking the best layer at each level, and stopping when the improvement is less than some threshold epsilon. Okay, so let's talk a little bit about results. If we're talking in a scarce data regime, which we don't have enough data, fine-tuning can result in overfitting, thus reducing the performance, but subtuning can get great results. So what we see here is on the x-axis the number of samples that we trained on, and on the y-axis the performance. As you can see, linear probing is much better than fine-tuning on the low data regime because we achieve overfit in the fine-tuning. But sub-tuning performs very well, starting from a few hundred of samples up to lots of thousands. We show this also on a different data set of VTAB 1K, comparing also to head-to-toe and LoRa. Great. So we did this also for distribution shift from CFAR to CFAR 10. The distribution shifts look like this, basically corrupted data with different methods. And we can see the results here. So this is the results for every data set, and we're comparing ourselves again to fine-tuning and linear probing, and also to some competition called surgical. We see that we get state-of-the-art performance on most of the data sets, and on average, obviously much better. On this plot, we can see how affects the number of blocks that we use to sub-tune on the performance. So we can see that using only 2 blocks, we get better results than fine-tuning. Okay, so let's talk about our final thing, multitask learning. Sub-tuning is ideal for multitask learning because it achieves high algorithmic performance, and it allows us to add new tasks on the deployed models. This is something that I think many of you have noticed, that once we have a deployed model in our system, it's very hard to add a new task to it. We need to retrain everything and keep the performance. So what we're saying, we can pay only low inference cost, but add a new task. So how would we do it? Let's say in a basic scenario, we just have a frozen backbone, and when we want to add a new task, we're just training a new head on top of it. So this is very easy and very cheap, but it may get not good enough performance. What we're doing in sub-tuning, we're just adding a few layers in between. We're selecting the layers in a smart way, and then we have a simple trick of returning back to the regular network and concatenating the outputs on the batch axis. This way it allows us to parallel compute the whole network and get very good performance. So I'll show you the results. If we're using ImageNet to CFAR 10 transfer learning, linear probing will get almost 92% accuracy. But it adds only a small inference delay. If we're using fine-tuning, we're getting to almost to 97%, but we're paying twice the inference cost because we need to run 2 different networks on top of the. What will happen if we use sub-tuning? So on the x-axis, we see the added inference time, and on the y-axis, the performance. So if we look at the leftmost top dot, we can see that by adding 5% inference time, we can close almost the whole gap from linear probing to fine-tuning, get to almost 96% performance. So let's summarize everything together. Sub-tuning is simple yet efficient. It selects an hopefully optimal subset of layers to fine-tune. We use a greedy algorithm to improve performance, and it achieves a state-of-the-art performance on low data regime and also multitask learning with constraints on runtime. Fine-tuning profile is something very important to understand that not all layers are created equal, and different layers affect the performance in different ways. And finally, it is ideal for multitask learning on top of a deployed model. It adds a low inference cost, high performance, and no effect on the existing task. Thank you.
Very nice work. Any questions? Yes, please. You need a microphone? You're bringing it. Okay.
Hi, thank you. What is the metric that you select the layers in the tuning profile?
So we're just using the accuracy. We're just training all the networks, all the layers, and we pick the best one that affects accuracy.